In this section, we'll be introducing axiomatics and proofs. So one of the common themes that the textbook that we're going to be doing and our class just in general is going to emphasize is that discovery in math is both enjoyable and also can be viewed as a useful tool in math. So why is discovery a useful tool for us? Like how could this be useful? Well, let's look at an example. So in this class, we're going to be doing a lot of work with axiomatic systems. So the gist of it is going to be we're going to be building up Euclidean geometry as well as some other forms of geometry, which we'll talk about later. We're going to be building up these geometric systems starting with axioms. So let's look at an example of a system with three axioms and see if we could answer some questions about it. So the first axiom is that each line contains exactly 4 points. Second axiom is that each point lies in exactly 2 lines. The third axiom is that 2 distinct lines intersect in at most 1 point. Okay, so our system has lines, it has points, and then our axioms are telling us some properties about lines and points. Keep in mind, lines and points are just undefined terms here. We'll be talking more about undefined terms in axiomatic systems later, but anyway, so lines contain 4 points. Points lie in exactly 2 lines, and 2 distinct lines intersect in at most 1 point. So that means that like they're either going to intersect once or they're not going to intersect at all, which would mean they're parallel. Parallel lines means that they don't intersect. So one question that you might have in the beginning is, all right, well, do parallel lines even have to exist? Or can we even have parallel lines in an axiomatic system? Do they always have to exist in our axiomatic system? So that's a question that you might ask based off of this simple axiomatic system: is do parallel lines exist? And so this is where discovery comes into play, because discovery can be used as a tool to figure out whether or not parallel lines exist, or like to kind of give you something to work with. So what do I mean by that? Well, the way that we would use discovery as a tool is we would take this axiomatic system and just play with it and come up with some ideas, some pictures for what a system that satisfies these rules could look like. So here on the left, I have a line drawn, and this line contains 4 points. So this is just a schematic picture of a line here in our system. So this line contains 4 points. So good. Right away, we have 1 line and 4 points on that. So at this point, our first axiom is satisfied. And then if we look at our second axiom, our second rule, each point lies in exactly 2 lines. All right, well, is that true? So this point right here lies in this line, but there is not a second line that it lies in. So this line by itself does not satisfy this axiomatic system because it does not satisfy the second axiom. So we have to do more. We have to add in more lines to fix this, right? And then axiom 3 says that 2 distinct lines intersect in at most 1 point, right? So we can't have things like this being a line, for example. These 2 lines would intersect in 3 points right here. So axiom 3 tells us that something like that can't happen. Okay, so we could easily just satisfy axiom 3 by just making sure that all of the lines that we draw are just going to be straight lines, right? As long as we don't have any curve to them, they're not going to intersect in more than one point. So anyway, let's try to add some lines to this picture here in a way that satisfies axiom 2 and continues to satisfy axioms 1 and 3. So let's just add a line at the start of this point right here. And let's just put 4 points on it. And then we could do the same for this second line. So we have 4 points on that line, and then maybe 4 points on this line right here, and 4 points on this line right here. So right here we, so now every one of the 4 points on our first line that we started with is contained in exactly 2 lines. But that is no longer true of the points that we just created, right? So all of these other points lie in exactly 1 line. So we need to add some more lines here. And so there are some options for what we could do here. So the first option is that we could just draw lines like this. So this actually ends up being like a really convenient way to do this. So if I just draw a line between through these 4 points right here, and then through these 4 points right here, and through these 4 points right here, that just really conveniently gives me that each of these points is going to be contained in 2 lines, the horizontal line and the vertical line that is contained in, right? And we're still satisfying the third axiom, which says that 2 distinct lines intersecting at most 1 point. Each horizontal line is going to intersect a vertical line in exactly 1 point. And the first axiom, each line contains exactly 4 points, is still satisfied because every new line that I created still followed that rule. So this is one system that you could create. This is not the best picture of it, but oh well. And let me get rid of this because there are more things that we could do. So another thing that we could have done here, could have done this. So let's draw that line right here. I'm actually going to draw this one pointing downwards. Doesn't actually really matter. It just changes how the picture looks, but it doesn't really change the math. Okay, so you could do something like this. And then you could, what could you do? Well, now you can just draw new smaller lines coming out of each of the points. Like I'll start over here. So I'm going to draw another line coming out of here, here, and here. So let's do, this one will go to the right, this one will go to the left, this will go to the right, and then put points on each of those. And then we could do the same over here. And we could do the same up here. And then the same up here. And then just imagine that I'm putting points on all of these lines. I won't bother because it's quite a lot of work to do so. And then, well, what do we do from here? Well, we've just created even more points that we need to draw lines coming out of. And you might think that that's a problem, but I don't think that it is, because you could just, in theory, just say that like, well, we're just gonna continue this construction infinitely. So we're just gonna keep on doing this as many times as we need to. So here I'll have lines coming out like that, and then lines coming out there, and then lines coming out there. Same over here. Same over here. And here. And then I would do the same up top, and then also coming out of these lines here, and then you just kind of keep going with that, right? So you just do that process ad infinitum, just as infinitely many times. Just keep doing that process, and you end up with something that it's called a fractal because you're just doing the same thing over and over and over again. Like if you zoom in on this picture, you just kind of keep seeing like the same picture that you had before. Yeah, so we just call that sort of thing a fractal. But don't worry too much about that. We're not going to be doing anything with fractals in this class for the most part. Just understand that there are different ways that you could go about constructing a model. So anyway, this looks a little messy, so I redrew these two models down here. So we had the 4x4 grid that we did first, which is a bit simpler than the fractal pattern, the infinite fractal pattern. This is the one that shows up in the book, by the way. This 4x4 grid does not show up in the book. The book really liked the fractal pattern, and so wanted to talk about that one more, which is great. So anyway, back to what was our original question? Our original question was, do parallel lines exist? Right? So a parallel line, or a pair of parallel lines, is just a pair of lines that do not intersect. All right, so for example, this line right here is not parallel to this line right here, but it is parallel to all of the other horizontal lines here. So there are 4 parallel lines right there. So in this system, there are parallel lines. All right, cool. Well, what about in this system over here? Well, this line right here is parallel to this line and this line, and also this line. And, well, it's parallel to every line that it does not intersect. In fact, the only line drawn here that this does not intersect is, draw it in red, I guess. Well, maybe green. This is the only line that that blue line does not intersect. So those lines are not parallel. Similarly, if I wanted to look at this line right here, what lines are not parallel to it? Well, this line is not parallel to it. So I have this orange line. And then there's this line right here, and this line right here, and this line right here. So well, those 4 lines intersect our green line. And so those lines all intersect it. But otherwise, there are infinitely many other parallel lines to our green line. So yes, parallel lines exist, right? So one question that we haven't answered, though, is, does any model for our axiomatic system have to include parallel lines? Right? So that is less clear. It is less clear to me that no matter what model you come up with for our axiomatic system, that there's going to be some parallel lines in it, right? So commonly you'll be handed some axiomatic system, and you'll want to know, all right, what properties must any model for these axioms satisfy? And so to find these properties, typically you would just start with a discovery approach and just start kind of creating models and figuring out what would these models possibly look like, and then start noticing patterns in them. Right? You could ask based off of those axioms, like, must any model be finite? Must it be infinite? And then after drawing these models, you would say, all right, well, it doesn't have to be either of those. And we haven't even concluded whether or not every model must have parallel lines in it, because I've only drawn 2 models. We don't know if this is like every possible model that you could come up with. I'm sure that someone out there could, maybe one of you guys could come up with a different model that looks distinct from these two, right? So, but to find properties that any model must satisfy for that axiomatic system, you would actually need to start with those axioms. Well, first have a guess for what those properties would be, and then take your axioms and actually prove that those properties must hold just based off of those axioms that you work with. And that's going to be a common theme for what we're going to be doing throughout this class. So yeah, that's it for this part. Thank you for listening.